when we were multiplying and adding on the plane, you're going to see that this has a nice end result here. So here's what we're going to talk about. So our objective today is to be able to multiply, divide, and find powers of complex numbers in trig form. I call it trig form because that's the way I was taught. What's the other name for trig form? Polar form. Okay, so you can also call that polar form. They're both the same thing. Okay, so here's what we're going to do. We're going to do some binomial multiplication to start off with. So I'm going to walk through this with you together because you're going to like the assignment. The assignment's pretty easy. What we want to do is we want to walk through and we kind of want to discover, hey, how does this work and why does it work the way that it does? So we're going to do this problem to begin with. We're going to take this complex number and we're going to raise it to the third power, which means we need to take this. And remember, it's kind of convention that we put the i's in front. And I'm going to multiply it by itself. And then I'm going to get the answer and I'm going to multiply it by itself again. Okay? So we're going to multiply -1 times -1, so we're going to get 1. Then we're going to do -1 times -I radical 3, so that's -I radical 3. Multiplying here, that's going to be -I radical 3. And multiplying here, I get, let's see, that would be an I squared, and a radical 3 times a radical 3 would be a 3, right?
Yeah. So it's negative.
So this counts as a -3, right? So if I put the two of those together, I get -2. And I've got two of these, so this is -2I radical 3. Are we right about that?
Yes.
Okay, so here's what I'm going to do. I'm going to take this preliminary answer. I'm going to take that one, so that is -2 minus 2I radical 3. And I'm going to multiply it by that original binomial because I needed to cube it. I need to multiply it by itself 3 times. So this is -1 plus I radical 3. Okay, everybody okay with that?
Yeah.
Okay. So I'm going to multiply here 2. I'm going to multiply here -2I radical 3. I'm going to multiply here. This is a negative times a negative, so that's going to be a positive. And I've got a 2I radical 3. Well, that's kind of cool. That's going to work out nicely. And then we need to be careful on the last one. So here's what I get. I'm going to have a negative and a 2, and an I times I is an I squared. And then I'm going to have a radical 3 times a radical 3. Is everybody okay with that? Just step-by-step simplification. So these two are cool because they're exact opposites. It just so happens they go away. So I end up with a 2. Radical 3 times radical 3, that's a 3. So would everybody agree I've got a -6I squared? And Colson, what does that turn into?
Just 6.
That turns into a +6. So after all of this ugly mess, we end up with 8. You take a weird complex number like -1 plus I radical 3, multiply it by itself 3 times, and you get the real number 8. That's crazy.
That is
okay? So we're going to find this by the time we're done. We're going to do this in a slightly different way. So here's what we talked about in the last lesson. Geometrically, we can represent multiplication of complex numbers in trig form by multiplying the moduli and adding the angles. Okay, Zach, if we're going to be using angles, what do we need to do in our calculator?
turn it to degree.
Make sure it's in degree mode, okay? So this is similar to one that we did yesterday. So I've got a diagram here that shows what's going on. So let me talk about the diagram really quickly, and then we'll run through and do the problem. So I've got this first complex number, 2 plus I. So I've got it graphed. So it ends up at this point right here, and we've got this theta, this angle right here. Then I've got this second number, 1 plus 3I, so it's located right here, and it produces this second angle, we'll call that theta 2, and it produces that modulus. If I multiply those together, then I end up with adding those two together, so I end up with theta 3 here, so this big angle, and I end up with the number -1 plus 7I, and I end up with this long modulus right here. So multiplying the two of those makes it this long, adding the two angles together makes that theta 3 there. Okay, that's what we talked about yesterday. Okay, so we're going to do some verifying here. So it says, consider the complex numbers z1, 2 plus I, and z2, 1 plus 3i. So those are the ones that we started with right here. It says verify the modulus of z1 is radical 5 and verify that theta 1 is 26.57 degrees. So let's go ahead and do that. So to find the modulus, we're going to do 2 squared plus 1 squared. So that's the square root of 5. So check on that one. Jack, how do I find theta? Oh, we got to know this. Wilson, help him out.
How about crew helps us?
How about crew helps?
You add them.
Nope.
Oh.
Tangent
D?
inverse.
Tan inverse of B over A.
B over A. So it's going to be the imaginary part over the real part. So this is going to be 1/2. So grab your calculator. We're going to make sure we're in degree mode.
Oh.
And we're going to do tangent inverse. Follow along.
Theta 3 by adding.
You're right about theta 3, but that's not what we were asking about. Okay.
Well, me and Jack weren't there for that thing. You know?
Oh, that's
Like,
too bad.
we were
D.
absent that day.
It's like 0.01 right?
Well, didn't we round it up? 26.57, isn't that rounded right?
No, now it's 26.56.
Oh, does yours say something different?
Yeah.
Ooh, that's weird. Okay, so yeah, fix it, will you? Okay, so this is right, 26.57, right? Okay, so check on the two of those. Okay, I'm going to freeze the screen. Would you verify on part B, would you verify that the modulus of Z2 is radical 10 and verify that theta 2 is 71.57 degrees? Does yours say 71.57? Okay, all right, perfect. I'm going to freeze the screen. Go ahead and do it.
Wait, imaginary over real. Oh, but that one's right. That one's right.
Si, will you pull the door shut? Crew, how's that verification coming?
Good.
I don't think we should.
I was eating, sorry.
Luke, did it work out?
Yeah.
Okay, verified?
I verified it.
Okay. So I'm not sure why. It's kind of interesting that it works out that the decimal portion of both of these is the same. Maybe coincidence. I'm not sure why that happened. Okay, but I got 71.57, so I verified this one. 71.57 degrees. And I verified that if we take the 1 and square it and the 3 and square it, I get 1 plus 9, so I get radical 10. So both of those check out. Yes? Okay, next part. We want to verify that multiplying z1 and z2 does give us this right here. So let's write down 2 plus I times 1 plus 3i, and let's see what we get. So we're going to do 2 times 1, 2 times 3i, that's going to be 6i. I times 1 is going to be I. And then I times 3i is going to be plus 3i squared. Hold on just a second. Dane, what does 3i squared count as? -3. So that counts as -3. So if I take the real components and I add those together, I get -1. And if I take the imaginary components and add them together, I get 7i. So that checks out. That verifies, right? Yeah.
So why would you do all that if you just accepted the modulus of both and then the multiply and see if the multiply becoming modulus?
So we're getting there. We're just verifying some things. So by the time we're done with this, we're just making sure, yes, this does actually work. We've done it with a problem and we've double checked everything. Okay, so the last verification that we want to do on this one is verify that the modulus is radical 50. So if I check this, I take -1 and I square it, and I take 7 and I square it, so I get 1 plus 49. I get radical 50. That checks out. This one's a little more interesting. Okay, so would you find the angle, find theta 3 for this?
Doing it the cool way.
Oh, okay.
You're going to type in tangent inverse,
What's weird about
and you're going to do the imaginary part over the real part. So you get 7 over -1. So I'm going to grab the calculator and I'm going to type that in. So we're going to do tangent inverse of 7 divided by -1. And again, of course, you could, if you're dividing by 1 or -1, you could just type in tangent inverse 3, tangent inverse -7. But I hit enter and I get this.
Dude, I hate that.
Okay? So does anybody remember what that says? We talked about this. That is not the answer, but it helps us get the answer.
No.
And I would love it if you could use the right vocabulary words to describe this. Zach, what do you think?
So that's the angle of the line, which is actually in the third quadrant
Uh-huh.
of the thing. So you have to add 180 degrees to the number to be able to create the actual degrees from 0.
The actual angle from 0, okay? So it's actually down here, and we want it, it's actually in quadrant 4. We want it up there. So you said we have to do what?
You have to add 180 degrees.
We have to add 180 degrees. The vocabulary word that he didn't use is this is the size of the reference angle, okay? So the reference angle right here is, 81.86 degrees. So whether you take 180 and subtract that, or just say, oh, it's the answer's down here and I'm going to add 180, doesn't make any difference. I'm just going to add 180, and we end up with this, okay? So 98.13. So I'm going to draw an arrow, not an equal sign, but we're going to say 98.13 degrees. Okay, so we verified that. Hang on one second. Okay. Does what we talked about yesterday work in this case? Not does it look like it worked like we asked you to do yesterday. On the back side of yesterday's assignment, all you had to do was say, yeah, it kind of looks like it would work. What we're doing today is we're saying, hey, if I take the two moduli, if I take radical 5 and I take radical 10, so if I take the two of these and multiply them together, do I get that? Yes, I do. If I take these two angles and add them together, do I get that? So would you throw that into your calculator? Would you do 26.57 plus 71.57? Do you get this, give or take some rounding error? You do, don't you? Okay, so does this multiplication method work? No doubt about it, right? Okay, now, it's not very interesting for using stuff like this if you have to do all of these changes, but it is kind of cool if you get to do this. And remember when I said it was going to be kind of nice doing the homework? Okay, so here's what some of your problems are on your homework. It says perform the operations, then write the answer in standard form. In other words, write it in rectangular form. So the cool part is these are given to us in trig form. They're given to us in polar form. Please. So to get the answer, it's this quick. There's none of this stuff. There's no multiplying like this. There's no multiplying like this. We're going to take the two of the moduli and we're going to multiply them together, and we're going to get 20. Then we're going to write cosine of, we're going to add the two of these together. So this is going to be 345 plus I sine 345. And if we could just leave this in this format, it says it wants us to change it into rectangular form, you'd be done. So on the calculator, we're going to grab the calculator. I'm going to shrink this down so we can do this really quickly. So I'm going to type in 20 cosine of 345. Now, I'm using the calculator and we're going to approximate because is 345 a common angle? It's not. 330 and 360 are. Okay, so we're going to type that into the calculator and I get 19.32 plus, now we'll do the imaginary part. So So I'm just going to recall this. I'm going to change that to a sine. And I get minus. So minus 5.18i. Put a box around that. And that's our answer.
What? That was so easy.
Is that easy?
It is.
And we
Now,
did that.
if we had to take it from rectangular form, convert it to polar form, then do this and then convert it back, then it's kind of a pain in the butt. But if it's given to us in rectangular form, see how easy that is? We don't have to do all of the distributing and collecting like terms and all that sort of stuff and worrying about checking with Dane, hey, Dane, what does 3i squared count as? We just write this down and we write down the answer. And the next one's even easier. I do have a little warning on this one, so I'm going to make this one a little bit bigger. We multiply the two of those together, so that's going to be 32. And then it's going to be the cosine of, let's see, 270 plus 150. If I do 270 plus 150, I end up with 420 degrees plus I sine 420. Oh my gosh. Okay. Now, over here in this box, this is a convention. This is a perfectly good answer. Whoops, let me get rid of this. Remind me later. This is a perfectly good answer. This means we add these together, we get to 420 degrees. So we go around the circle, one full circle plus a little bit extra. By convention, we normally say these angles when we're writing in polar form, trig form, cis notation, however you want to call it. We usually use angles that are between 0 and 360. So what I'm going to say is, look, 420 goes around the circle once plus a little bit. I'm going to subtract 360, so we end up with this. 32 cosine of 60 degrees plus I sine 60 degrees. Okay?
60, 90.
So this would be the answer if we wrote it in polar form. But we can figure out these answers without using a calculator because the cosine of 60 degrees is 1/2. And the sine of 60 degrees is radical 3 over 2. So then I can multiply both of these by 32. And I end up with, correct me if I'm wrong, this is 16 plus, let's see, 16i radical 3.
Yeah, what if I do it in decimal?
Yeah.
So what if you just plug in the 420, the cosine of 420 plus I sine?
It would give you the decimal equivalent would be exactly the same. In this case, because your calculator is going to store all the decimal accuracy either for the sine of 420 or the cosine of 60 or whatever it happens to be, it's going to work out to be exactly that. Okay.
Wait.
The radical 3 it's not going to work with, but the 16 is going to work fine. Yeah.
So if I would like want to do it in decimal form, it'd be wrong.
Let's stick with the way we've normally done this. If it's a common angle, we want to write it in exact form. If it's not a common angle, but you're here now, and I'm telling you now. Okay.
I just didn't know that
Yeah.
because I was absent.
Why isn't there like a thing on like your calculator when you have like a decimal to turn it into like a
Turn it into a radical.
yeah?
That would be very cool.
Because there's like
Okay.
fraction in there.
That would be very cool. Okay, so take a look at this next box right here. Do not say anything out loud. Would you just read it to yourself?
Dividing the
Oh. So if when you're multiplying them, you multiply the moduli and you add the angles, does anybody want to take a guess at what we do when we divide complex numbers? Caleb.
Divide the moduli and subtract them.
Very good. Divide the moduli and subtract the angles. Okay. So we're going to come down here and we're going to go ahead and do this. So on this one, the answer would be 5, and then it's going to be cosine of, let's see, 345 minus 45. So that's going to be 255 plus I sine 255. And the great part about this is once you've done the arithmetic for one of the angles, you know it's the same for the other one. And then on this one right here, this is going to be 2, and let's see, cosine of, if we subtract, that's going to be 120, I think. So we didn't have a geometric way to represent that when we kind of covered this yesterday. Now we do. You can kind of visualize how this would happen. Now on this one, it does say change this to rectangular form. Okay, I'm not going to make you do that on this one just for time, but we would just do 5 cosine 255 for the real part, and then 5I sine 255 for the imaginary part. Wilson, would it be okay to have decimals on this one?
Yeah, because it's not common angles.
Very good. Would it be okay to have decimals on this one?
No.
No, 'cause
No, it
it's
wouldn't.
common angles.
Okay, do not say anything out loud. Cosine 120. You should have that number in your head.
Oh, wait. Wait. Oh.
Andy, you know what it is? It is 1/2. Is it positive or negative? It is negative. Okay. Sine 120. Do not say anything out loud. Megan, you got sine 120?
No.
D?
Radical 3 over 2.
Radical 3 over 2. So this would be plus I radical 3 over 2. Then you distribute. The 2's are going to cancel. This is going to end up being -1 plus I radical 3. Okay? Now, if you want to change the other one in decimals, that's fine. Would you flip the page over?
No, they're fine.
That is going to be something crazy.
Oh wait, didn't we just do this?
We did something similar to that.
No, like on the back.
On the front?
Yeah.
Yeah.
the
Okay.
Same exact problem.
This is the same exact problem. I would just want to demonstrate something. So we want to verify that -1 plus I radical 3, so -1 plus I radical 3, is this number right here in trig form. So -1, this is radical 3. To find the modulus, you would do -1 squared and radical 3 squared, so that's going to be 1 plus 3, so that's going to be radical 4. Everybody agreed that the modulus is 2?
Yeah.
Okay. We could have done it this way. If you recognize that this is the short leg and the long leg, you double the short leg. You'd have the hypotenuse would be 2. We should recognize that this is the longer of the 2 legs on a 30, 60, 90. So the reference angle is 60 degrees, which means from standard position, the direction angle would be 120 degrees. So does everybody agree that we've verified that if you graph this on the complex plane, you can represent it in trig form with a modulus of 2 and a direction angle of 120 degrees?
Yes.
Everybody good with that? Okay. All right. So down here, this is a French guy named de Moivre. You can say de Moivre. Okay. A lot of people pronounce it many different ways. He came up with this thing that said, hey, if you want to raise a complex number to a power, you could do it the way we did in the warm-up, multiply it by itself repeatedly, or you could take advantage of the fact that we end up just multiplying the modulus by itself over and over and over again, and then adding the angle to itself repeatedly. So here's what happens. If you're taking a complex number in trig form and raising it to a power, you end up raising the modulus to that power, and you end up multiplying the angle by whatever that power is, because you're adding it repeatedly to itself. So here's the cool part about this. This is the problem that we did on the front, but we're going to verify that the answer is 8. Remember, it turned out to be 8. We're going to verify the answer is 8 by using de Moivre's theorem. So de Moivre's theorem says this. If we're going to take this and we're going to raise it to the third power, we're going to raise that to the third, and we're going to multiply this by 3. So this is going to be 2 to the third cosine of 3 times 120 plus I sine 3 times 120. So we end up with 8. Correct me if I'm wrong. Cosine of 360 plus I sine 360. By convention, we don't use the angle 360. We change that to 0 degrees. So this is going to be 8 cosine of 0 plus I sine of 0. Do not say anything out loud. If you need to visualize it on the unit circle, 0 degrees is right here, and the coordinates 1, 0. So Jack, what's the cosine of 0? 1. And Angela, what's the sine of 0?
0
0. So if I multiply here, I end up with 8 plus 0i. So I end up with 8. And isn't that a heck of a lot easier than what we did in the warm-up?
It's so much faster.
It is. Okay?
Crazy.
So slide down here.
Yes.
Got 2 more problems to take a quick look at, and then we'll be done. I'll hand out the assignment. We want to take this one and we want to convert it into trig form so that we can use de Moivre's theorem. That's going to make it a lot easier. Way easier than multiplying the number by itself 4 times. Way easier than multiplying by a number by itself 5 times. So let's visualize where this would be. Negative radical 3, or sorry, negative 3 radical 2 plus 3i radical 2
Oh,
Recognize that? Luke?
It's a 45, 90.
It is a 45, 45, 90, which means we multiply a leg by radical 2 to get the hypotenuse. And if you multiply by radical 2, that's going to be 3 times radical 2 times radical 2. So correct me if I'm wrong, that's a 6, right? With a 45-degree reference angle, so what's the direction to begin with? 180 minus 45. Common angle. 135. Okay? So we're going to take 6 cosine 135 plus I sine 135, and we're going to raise it to the 4th power. So that's going to be 6 to the 4th. And would it be okay if I wrote this?
Ooh, that's devious.
Cosine plus I sine. Cis notation. 4 times 135.
what did you just do?
540.
540.
540.
So this is 6 to the 4th, and then cosine 540 plus I sine 540. By convention, we ought to subtract 360.
And then you get the answer that's correct.
Wait a minute. Isn't that a nice number?
180.
180. So 6 to the 4th, and then this would be cosine 180 plus I sine 180.
That's a 7.
You can leave it like that, but would it be very difficult to change that into rectangular form?
Nope, no, it's just
Especially not since we know what the sine and cosine of 180 degrees are.
true.
Okay? Hang on one second.
Do we need
Okay, so this one would be 6 to the 5th, and then 5 times 135.
Yeah, I don't know what form.
What's 5 times 135?
675.
675. We're going to take off at least 360, and we're going to end up with 315. So this is 6 to the 5th cosine 315 plus I sine 315. Okay, and again, could we change this to rectangular form? Would that be very difficult? Not very difficult, because both 180 degrees and 315 degrees are common angles. We know what they would be. We can answer them in exact form.
What would it be?
Okay. Let's see. This would be, cosine would be radical 2 over 2, and sine would be negative radical 2 over 2.
I don't know, 6.
And for 180, what's the cosine of 180?
Negative 1.
Negative 1. And what's the sine of 180? 0.
And
Okay.
it would be
All right. Now,
7,776.
we're just about done. Okay. Do not say anything out loud. Would you read that last paragraph to yourself?
Jack doesn't speak math.
I don't know any of those.
Okay. Okay, listen up, then I'm done. When we find inverses, inverting a process is usually much more complicated. Okay, but if you look at that formula right there at the top, we raise the modulus to the r, or sorry, to the n, and we multiply the angle by n. You want to take a guess at how we take the square root of the third root of the fourth root?
We put a square root over r time, and then
We take the root of the modulus and
you times the number of however times, like cube or square or whatever, times by divided by the cosine.
you divide it by whatever you're doing. Now, here's what's more complicated about this. Zach has the general idea of how you'd find roots of complex numbers in trig form. The problem is when you find the roots, just like when you take square roots, if you put a square root in a problem, what else do you have to put in there? You have to put in the plus or minus, right? If you have to put the plus or minus, that means there's two answers for each one of those. So if you're finding a cube root, it turns out there's actually 3 cube roots. If there's a fourth root, there's actually 4 cube roots. And finding those is not horribly complicated. It is based on this. It's got some really cool properties, but that's the basic idea. Okay?
When do we learn that?
You'll learn that when you take an actual trig class. Okay? All right, so I'm going to stop this.
I'll never learn that.
No, you'll learn it. You're going to take 1060.
I think I'm gonna take math.
I'll take
class.
1050, but not.
I remember looking at
to lock away all this knowledge of trig before you take calculus.
Hey, how much
And
skips do we
begin
get?
seeing it for the second time.
Skips 4?
Let's see. Would you look at the back, please?
Can we skip 5?
Oh man.
Whoa.
Wait, can we skip like 1, 2, 3? Can we skip 3 or 4?
Would be living on the street.
7
Oh yeah.
No, this is easy. What? No, this is easy.
Mr. Laws!
Third law.
I think
What
you'll
about
be
our
okay.
quiz?
What?
What about our quiz?
100
No.
points?
No, are you passing it out?
Oh, the quiz?
The practice?
The practice quiz? I think you'll be okay. It's a pretty easy quiz.
Wait, I don't know how to do 4.
Mr. Laws! You divide.
Yeah, but it's 0 divided by 4. 1 divided by 4.
There you go. I won't tell anybody.